Welcome back to the LCC Fusion Project series. In the last session, we took a deep look at the block breakout board, the part that organizes block feeder wiring under the layout. Today we're moving one level deeper, into the actual brain of block detection, the BOD card itself. So if the breakout board is the wiring hub, what exactly does this card do?
This is the card that actually tells the system whether a block is occupied. It reads the tiny electrical signal coming from each block and converts that into a clean digital value. From there, it reports those results to the node card, and the node card publishes the occupancy events onto the CAN bus network. So think of the BOD card as the translator. The breakout board brings in the raw wiring. The BOD card interprets the electrical state of each block. And the node card handles communications. All three pieces work together, but this card is where the detection actually happens.
Alright, the breakout board handled the wiring, and this one handles the logic behind it. Let's dive in. Before we go deeper into the BOD card, let's just anchor what we talked about last time, the block breakout board. I want to make sure I'm still seeing the whole system correctly.
Exactly, and this recap is important. The block breakout board is the physical wiring layer of block detection. It doesn't measure anything, it doesn't send anything on the CAN bus, it doesn't make decisions, it simply organizes where all the block feeders land. It also routes the gap rail feeders, rail B, into a clean, isolated connection so each block can be detected independently. Optional trickle detection and the optional snubber add flexibility, but they're still purely electrical features.
Right, so that board just gets all the block wiring under the layout into one neat place.
Exactly. The breakout board prepares the signals. The BOD card, this card, is the one that interprets those signals and decides whether a block is occupied. The node card then takes that information and publishes it onto the CAN bus.
So the breakout board gives us the wiring, the BOD card gives us the logic, and the node card gives us the communication.
Perfect summary, and that's exactly the flow we're following in this episode.
Before we look at the components, let's place the BOD card in the bigger picture. What exactly does this card do?
The BOD card sits in the middle of the block detection chain. The breakout board sends it 8 simple voltage signals, one from each block. The BOD card reads those signals, decides whether each block is occupied or clear, and then feeds those results into the port expander.
So this is the first part of the system that actually does something with the block signals?
Exactly. This card performs the actual detection. Once it determines the state of all 8 blocks, it reports the results to the node card using I2C. The node card then publishes the occupancy events onto the CAN bus so the rest of the layout can respond.
So the flow is breakout board BOD card node card CAN bus.
Perfect summary. The breakout board handles wiring. The BOD card handles detection. The node card handles communication.
Before we get into the detection circuitry, what are these LEDs over here on the left? What are they telling me?
Those are the power and occupancy indicators. They're your quick visual dashboard for what the card is doing. The power LED tells you the card is alive and receiving clean voltage from the node bus. And each block has its own occupancy indicator, so during testing you can immediately see which blocks the card believes are occupied or clear, without even connecting the node card or looking at the CAN bus. Right next to those indicators is the DCC to DC front end. Each block's DCC current from the breakout board passes through a resettable fuse, a bridge rectifier, a protection diode, and a sense resistor. That chain converts the current to DC so we can safely detect block current. Right next to that is the current detection stage. Each block has its own optocoupler/comparator, and that device watches the tiny voltage across the sense resistor. If there's enough current flowing in that block, the optocoupler reports it as occupied. If not, it reports clear.
So the actual occupied or not decision gets made right there in that optocoupler section.
Exactly. The optocoupler is the component doing the real detection work. Then in the center is the MCP23017 I/O port expander. That's the chip that collects all 8 detection results and presents them as clean digital inputs for the node card. Using this chip allows a very high number of inputs to be gathered across the layout and funneled into a single node card, making the whole detection system scalable without adding complexity.
And on the right, that looks like the address switch?
Exactly. That 3-position dip switch, SW1, and address selectors, JP1/JP2, let you set the I2C address so multiple BOD cards can coexist on the same node bus without conflicts. Right next to it is a small EEPROM. That's how the node card identifies what card is plugged in. It's all part of Fusion's plug-and-play system. Then down at the bottom is the node hub bus edge connector. That's the interface to the node card, bringing in power, the I2C data lines, and tying everything together with the rest of the Fusion system.
It's interesting, the layout feels familiar now. Everything has its own zone, just like the breakout board and the node card.
That's exactly the goal. Consistency makes it easier to build, easier to troubleshoot, and easier to teach.
Okay, here's the bottom side of the card. And I'm noticing something again, just like the breakout board, there are no components down here. Why leave an entire side completely empty?
That's intentional. Keeping the bottom side completely free of parts makes SMD soldering much easier. When you run this board across a hot plate or use hot air to solder the surface mount components on the top, the card sits flat and nothing on the bottom heats up and falls off. All soldering is done on one side, the top.
Alright, that makes sense, but I also see some text and labels down here. What are those for?
That's the informational silkscreen. Even though the bottom has no components, it becomes the reference surface when the card is plugged into a node hub or stacked with other cards. The silkscreen includes orientation reminders, block identifiers, and, importantly, I2C address information.
Right, so let's talk about that. I know the port expander needs an address. How does the address work on this card?
Great question. Every device on the node bus that uses I2C must have a unique address, and that applies across both bus A and bus B. The BOD card uses the port expander, which supports addresses 0x20 through 0x27. The port expander provides 8 possible addresses total, 0x20, 0x27, shared across all cards on both buses. In theory, that means you could have up to 16 BOD cards, 8 on bus A and 8 on bus B. But in practice, other Fusion cards also use this same address range, like the output card and the digital I/O card. So you need to plan the addressing so no two cards collide.
So the silkscreen is basically reminding me, hey, make sure this address is unique and doesn't overlap with any other card on either bus.
Exactly. And one more important point, the I2C address you set with the dip switch has to match the configuration you enter in the CDI for this BOD card. If they don't match, the node card can't find the BOD card at startup, and no block detection will show up on the CAN bus.
Got it, the bottom is basically a cheat sheet, SMD-friendly, orientation hints, address reminders, and all the info you need during wiring and configuration.
Exactly. The bottom may be simple, but it carries the information that prevents the most common installation mistakes.
Alright, before we move on, how do we actually mount this card in a real installation? Does it just hang off the node card somehow?
Mounting in Fusion is very flexible, and the BOD card follows the same universal pattern as all the other cards. The primary method is to insert the card into the node bus hub. The hub provides the node bus edge connector, and the card slides in just like an expansion card in a PC.
And what if you need more than one card? Some layouts have a lot of blocks.
Exactly, and that's where the stacking system comes in. Each card has two corner holes, sized for 3mm by 11mm standoffs. You can stack multiple cards securely, one next to the other, and the standoffs keep everything aligned, rigid, and protected.
Nice, so you can build a whole tower of cards if needed.
Exactly. And if you prefer to mount the cards under the layout, the BOD card also includes two sets of mounting holes that accept two standard brackets which attach to a DIN rail. That's the same DIN rail style electricians use for panel boards. It keeps everything neat, modular, and very serviceable.
Okay, and what about actually assembling the card? Some people are hand soldering these, right?
Absolutely, and that's why the design uses DIY-friendly components. All the SMD parts are in large sizes that are easy to solder by hand, no tiny parts. The pads are generous, the spacing is forgiving, and all components are widely available, meaning you can source replacements easily if you ever need them. Even the silkscreen layout was chosen to help guide assembly. We'll cover building this board in another podcast.
So the whole card, physically and electrically, is designed to be approachable for anyone building it themselves.
Exactly. The mounting options make it flexible, and the component choices make it practical for DIY builders.
Okay, so we've talked about the parts on the board. But can you walk me through what actually happens when a train enters a block? What's the electrical journey?
Absolutely, this is a great moment to look at the entire signal flow. Everything begins when the block's gap rail feeder carries the DCC track voltage down through the layout and into the breakout board. From there, that signal is forwarded to the BOD card on one of the 8 block connections. That signal then moves through a protection and conditioning chain, a resettable fuse, to protect the sensing circuitry, a bridge rectifier, which converts DCC to DC so we can measure it cleanly, a protection diode, and finally, a sense resistor, where a tiny voltage drop appears whenever current flows in the block.
So the sense optocoupler is where we actually see the train via the current it's using?
Exactly. That's the point where the card gets its information. The optocoupler monitors that voltage drop. If it sees enough current flowing, it switches into the occupied state. If not, it stays clear. Next, each block's detection result goes into both the status indicators and the port expander chip. This chip gathers all 8 block statuses and presents them as clean digital inputs the node card can read.
And then the node card publishes that onto the CAN bus?
Exactly. The node card reads the port expander's inputs over I2C, converts each one into an occupancy event, and puts those events onto the CAN bus so the rest of the layout can react.
So that's the whole path, from the track itself all the way out to the automation logic.
Exactly. And once you see it as one clean chain, the rest of the board makes perfect sense.
Okay, so now that we know how the card works electrically, let's look at how everything connects. What are the main interfaces on this card?
There are really 3 important connections. First is the block input header. This is where the 4 block signals arrive from each of 2 breakout boards. Each input is already conditioned by the protection chain we talked about, so these lines are very clean and easy for the optocoupler devices to read. Next is the node bus edge connector. This is the card's lifeline. It carries the 3.3 volt and 5 volt power rails, ground, and the I2C lines that the node card uses to communicate with the port expander. It also passes CAN signals straight through, since the node card is the one that actually talks on the CAN bus.
And then there's the address switch, right?
Exactly. The I2C address selector, the dip switch and jumpers, let you assign one of the 8 port expander addresses, 0x20 through 0x27. These must be unique across both bus A and bus B, and they must match your CDI configuration so the node card can find the BOD card reliably. And right next to that is the EEPROM IC. This is how the node card knows exactly what card is plugged in and whether it's valid for that bus. It's all part of the Fusion plug-and-play system that keeps installation simple.
And the LEDs on the left? Those are just indicators?
Right, you'll typically install the power LED and the 8 occupancy LEDs. These make testing much easier because you can see the block states without a node card, serial tools, or any software.
So the connectors define how the card fits into the Fusion ecosystem, the block inputs, the node bus interface, and the configuration hardware.
Exactly. Those are the 3 connection points that make the BOD card simple, modular, and consistent with the rest of Fusion.
Alright, once someone builds this card, how do they test it? What's the first thing you should do before putting it into a layout?
Great question, and testing the BOD card is actually very straightforward. The fastest way is to plug it into the node bus hub so it gets power from the node card. The power LED on the left should come on immediately. If that LED is not lit, you stop right there. You either have a soldering issue or the node bus isn't providing power.
And what about the occupancy LEDs? Do those come on automatically?
Only when the card detects current. To test that, you connect a small test load to the breakout board input. This can be a resistor wheelset, a 1K, 2K resistor, or even a small lamp. As soon as current flows in that block, the matching occupancy LED should illuminate. If it doesn't, you know exactly which channel to inspect. And once the LEDs look good, the next part of the test happens through the node card. It reads the port expander over I2C and publishes each block state as an occupancy event on the CAN bus.
So you can actually watch the events being sent?
Exactly. You monitor messages via node card serial monitor, web serial, or even Bluetooth to see each block transition between occupied and clear. Or, use an LCC CDI event monitor tool. This confirms the entire chain, from the block input, to the optocoupler, to the port expander, to the node card, and finally out to the CAN bus.
So by the time you're done with this test, you're confident the whole card is solid before it ever touches the layout.
Exactly. It's a quick, reliable validation that the detection system is ready to go.
Alright, so once someone has this card built and powered up, what are the most common problems they'll run into?
There are a few patterns that show up over and over, and they're almost always easy to diagnose. First, if your power LED isn't on, the card isn't getting power from the node bus. That usually points to a power supply issue via the node card or node card bus. Next, if one of the occupancy LEDs stays stuck on or never turns on, that's a hint that something's going on in the detection chain for that block. It could be a solder bridge, a rotated optocoupler, or an issue with the sense resistor for that channel. Check all soldering and component type and orientation.
What about when the node card displays messages that it doesn't see the BOD card at all?
That's almost always an I2C address or EEPROM issue. If the dip switches are set wrong, or if another card is using the same address on bus A or bus B, the node card can't find it. And if the EEPROM isn't programmed, or isn't seated properly, the node card doesn't know what card type this is.
Is there a quick way to tell whether the node card is even seeing the BOD card on the bus?
Yes, that's exactly what the node card self-test is for. When you put the node card into its I2C self-test mode, it scans both bus A and bus B and reports which cards it finds, by address and type. If the BOD card doesn't show up in that list, you immediately know the problem is on the I2C side, address settings, wiring, or the EEPROM, not the detection circuitry itself. And if everything looks correct on the LEDs but no CAN bus events are showing up, that tells you the node card isn't reading the port expander or the card is not yet configured correctly. That means you either have an I2C wiring problem, a bus conflict, or the port expander didn't solder cleanly.
So all of these issues really fall into just a few buckets: power, detection chain, I2C addressing, the node card not reading the inputs or the card's configuration.
Exactly. Once you know where to look, the troubleshooting becomes very straightforward.
Okay, so now we know how the BOD card detects occupancy. But what does that detection actually accomplish on the layout? What happens with that information?
This is where everything ties together. The moment a block becomes occupied, the BOD card sends the state to the node card, and the node card immediately publishes an LCC occupancy event onto the CAN bus. And that single event can drive any number of actions across the entire layout. For example, your signal logic can automatically set a signal to red when a train enters a block, or clear it when the block empties.
So one detection triggers the whole system?
Exactly. You can have turnout logic that doesn't allow a route to line if the next block is still occupied. Lighting effects can change when a train enters a scene. Sound cards can play crossing bells or announcements, all based on occupancy events. That's the real power of the Fusion system, built on NMRA's LCC standard and LCC open source software. You're not just detecting trains, you're using occupancy events as inputs to logic that controls everything else on the layout automatically.
So the BOD card isn't just a detection tool, it's the starting point for real automation.
Exactly. Block detection becomes the foundation for fully automated signaling, routing, and behavior across the entire layout.
Before we wrap up, it's worth mentioning the foundation that Fusion is built on. We're not inventing a new messaging system here. Fusion stands on top of something that already exists in the hobby.
Exactly. Fusion is built directly on the NMRA's LCC standard, layout command control. All of the messaging, event handling, and configuration structures follow the same open specifications published by the NMRA. And underneath that is the OpenLCB open source software, developed by a community of volunteers for more than a decade. Fusion uses that stack for everything: the event model, the CAN messaging, the CDI system. It's all LCC under the hood.
And that means it works with other LCC systems, right?
Exactly. Because Fusion is LCC compliant, it's fully interoperable with other LCC-based products, signal controllers, button boards, throttles, sensors, configuration tools. Anything that speaks LCC will work right alongside Fusion. You can mix and match hardware from different vendors and the system still behaves consistently. Fusion simply extends that foundation with modular hardware and DIY-friendly design. But the credit for the underlying architecture belongs to the NMRA LCC team and the OpenLCB developers who maintain the standards and the software that make this level of interoperability possible.
So that brings us to the end of the BOD card. We've seen how it detects trains, how it plugs into the Fusion system, and how those occupancy events ripple out across the entire layout.
Exactly. The BOD card is the foundation for everything that reacts to trains, signals, turnouts, routes, sound triggers, animation, lighting, and safety logic. Once the BOD card reports occupied or clear, the whole layout listens. It's simple to assemble, easy to scale, and completely modular, 8 blocks at a time. Just plug in more cards as your layout grows.
All right, what's next?
Next, we move on to the BSD card, which takes everything we learned here and adds short circuit protection for each block. It's the next step in building a safe, intelligent block system for your layout.
Great, let's dive into that in the next session.